Hey everyone, welcome back to the video. So based on the last video that I posted, I just wanted to do a little clarification on when it would be best to use one method like elimination versus another method like substitution when algebraically solving systems. So some materials that I would really recommend is that you have a TI-84 handy, and then I would actually recommend that you print out these notes, which you can find on my website, Miss Lee's Math Stuff at .weebly.com. Alright, so let's just recap what we covered in the last video. So in the last video, we covered that there were two main algebraic methods for solving systems, right? And so the first method was elimination, which we remember how to do using this MASS acronym. So we first manipulate, finding the least common multiple. We add, subtract, solve, and substitute. And then for substitution, we use this PS3 acronym to help us remember how to do it. So we pick the variable that we want to solve for, then we solve for it, then we substitute that expression that we just solved for into our equation, and then we substitute that value in to find the other remaining value. And regardless of which one you use, they will both always work regardless of whatever system you have. But it's just that sometimes one method is going to be easier than the other, or one method is going to be more efficient than the other. And so we want to make sure that we're picking the most efficient method. So there are a few times when elimination would really be best. And the way that we determine when elimination would be best is by analyzing the coefficients. And so when our coefficients for at least one of our variables either have the same value and the same sign, or the same value opposite sign, or there's an easy to find least common multiple between the coefficients for our variables, then it's probably going to be best to use elimination. And this just kind of comes down to what elimination really does, right? We add or subtract to 0. And so in order to get rid of one of our variables, to eliminate it to 0, right, we need the coefficients of those variables to actually add or subtract to 0, right? So let's look at our first example. When I'm analyzing my coefficients for my variables, I'm going to first analyze my coefficients for x. So my coefficient for x in my first equation is -4, and my coefficient for x in my second equation is 4, right? If I analyze my coefficients for my y variables, my coefficient for y in my first equation is -2, and my coefficient for y in my second equation is +8. Now, if I look at my coefficients for x again, right, I see that they're the same value, but opposite signs. So that fulfills my second characteristic of when elimination would be best, right? And let's actually start our elimination process so we can see why this is a key characteristic for choosing elimination. So if I do that second step of my MASS method, right, remember when you're solving using elimination, you're using MASS. If I do that add or subtract, I'm going to add my two equations together. And so when I add them, right, I have -4x plus 4x, and that's going to eliminate to 0, right? Those two terms cancel out. And then I have -2y plus 8y, which is +6y. And then -12 plus -24 is -36. And then I end up with a single variable linear equation that's really easy to solve, right? And so I had my same value, opposite sign for my coefficients, so elimination was going to work out really easily so that I could eliminate that x variable to 0. If I look at my second example, right, I'm going to once again analyze my coefficients. So if I analyze my coefficients for my x, I have -3 and -9. And then if I analyze my coefficients for my y's, I have +7 and +5, right? And so if I look at my coefficients for my x, I see that there's a really easy least common multiple there, right? I can just multiply this entire top equation by 3 in order to change this coefficient for x to be the same value, same sign, right? So let me actually do that. I'm going to multiply this entire top equation by +3. So this is the m part of your MASS method, the manipulation part. And so when I do that, I have 3 times -3x, which is -9x, 3 times 7y plus 21y equals 3 times -16, which is -48, right? I just distributed the 3. And I didn't do anything to my second equation, so I'm going to just bring it down over here. So I have -9x plus 5y equals 16. And then once again, because I have these two variables, right, this x variable in both my equations, where my coefficients are the same value and same sign, I can very easily just subtract my equations together. And negative 9x minus negative 9x, it eliminates the x variable. And so I have 21y minus 5y, which is 16y, equals negative 48 minus 16, which is negative 64. And then once again, I end up getting a single variable linear equation that's really easy to solve. Just like how when we were thinking about when would elimination be best, we want to think about what we're actually doing when we're substituting. That's actually where our characteristics for when substitution will be best come from, right? So the two characteristics that we want to think about when substitution would be the easier method is if one of our variables has a coefficient of 1, which makes it easy to solve for, or if one of our variables in an equation, or both, is already isolated. And the key point of why we want to do that is because that kind of gets rid of those first couple steps in our PS3 method for substitution, right? So we don't really need to pick a variable to solve for, or we want to make solving for the variable as easy as possible, right? So solve and substitute variable, right? This is the key thing that you're doing when you're doing the substitution method, right? So let's look at this first example to see this in action, right? So I want to look at my variables in both my equations. So over here, I have negative 7x. Because my coefficient is negative 7, it's not going to be super easy to solve for. I'm probably going to end up with a lot of fractions, so I'm not going to worry about that. Negative 2y, once again, my coefficient is not positive 1 or negative 1, so it's going to be kind of hard to solve for that without ending up with a bunch of fractions. When I look at my x variable in my second equation, I see that my coefficient for x is actually 1. And I know that this is 1 because I don't actually see a variable, I don't see a coefficient there, so I know that that coefficient is 1. So I can probably very easily solve for this x variable. And so when I do that, I'm going to take this over here. I have 1x minus 2y equals 11. If I try to isolate my x, I can just add 2y on both sides. And then I get 1x equals 11 plus 2y. And then I can actually take this expression and substitute it into my first equation whenever I see an x, and then I'll end up with an equation that only has y variables, right? And that makes things a lot easier to solve. Another instance in which substitution would really be easier is if you don't even have to pick the variable and solve for it if that part is already done for you, right? In this case, y is already completely isolated, so there's no variable that you need to pick, and there's no solving that you need to do initially, right? Because it's already done for you. So all you have to do is take this expression that y equals, which is negative 3x plus 5, and just substitute it into your second equation whenever you see a y. So you would substitute it by doing 5x minus 4, and instead of writing the y, you would substitute in negative 3x plus 5 equals negative 3. And then you end up with an equation with only x, which you can very easily solve. And so whenever we're thinking about when substitution would be best, you want to just think about, what am I really trying to achieve when I'm doing the substitution method? And what you're trying to achieve is just isolating a variable and getting it into an expression that you could very easily substitute back in. And so sometimes there's no cut and dry case, right? It's really up to you to decide which one you like better. And so for something like an ambiguous case like this example over here, where both methods could feasibly work, the world is really your oyster. And so if we try to think about why would both methods work, right? If I look at, let's say that I'm looking at my x variable, right? I see that my coefficient is 1 in my first equation for x, and my coefficient for x is 2, right? I see that there's a pretty easy least common multiple going on here, so I could really easily manipulate this top equation by multiplying it by 2. However, if I just look at my my y variables, and if I look at the coefficients for y, right, I see that my coefficients for y are the same value, just opposite signs, right? They're both 1, but they're just opposite signs. So I could easily use elimination. Another thing is that I have one variable like x over here in my first equation that has a coefficient of +1, so I could very easily just solve for x. And similarly, in my second equation, I have y with a coefficient of +1, so I could, once again, very easily solve for y. So I could really easily do substitution as well. So I hope that cleared some things up about when it would be best to use elimination versus substitution versus any other method when you're solving systems of equations. The main point here is really it doesn't matter what method you use unless it's specified that you have to use one method versus another. As long as you're maintaining properties of equality, it should work out fine either way. But if you need more practice, there's a link in the description below for a Desmos activity that you can use to actually kind of hone in that skill of trying to find the most efficient method to use.